Hello, how are you? This is Mike here, and in this video we're going to discuss something called a polynomial. A polynomial is a special type of function. So if we think about functions being up here, and they make up a whole bunch of different types of graphs. There are a whole bunch of different types of equations. A small piece of them, where if we pull out a small piece, we would call this piece polynomials. There are many different types of functions. We could also pull out a small piece over here, and we could say that this could be rational functions. Rational functions, that's just another type of function. If we were to pull out a small piece over here, if we were to pull out a small piece of our functions over here, we could call these radical functions. Radical functions. There are many different types of functions, but specifically in this video we're going to talk about polynomials. Poly means many, nomials means numbers or many terms. So this is something that we're going to see that could have many terms, but however, don't let the name poly or the prefix poly mislead you. It doesn't necessarily have to have many terms. So let's go ahead and just do well, I don't want to say a general definition, but let's go ahead and do a definition of the term polynomial. We'll go a little more math oriented here. So polynomial. So we're going to let piece of x exist as a polynomial, and here's where it gets a little mathy, but don't worry, we'll go over it together, such that p of x equals a sub n. We say this term right here, we say a sub n. And that stands for subscript, a subscript. A sub n is a subscript n. So this is actually an n that is smaller, n is a subscript of a. And then we say we have x to the nth power. So now the n becomes the exponent. And in our next term, we're going to have plus a of n sub n minus 1, x to the n minus 1 power. And we're going to continue on at this pattern. And I know this might seem a little foreign to you now, but I do like to expose people to some of this math nomenclature. Because that way when you see it in textbooks or if you see your professors talk about it, it's not so foreign. These guys right here we're going to call ellipses, and they just mean continue on in a similar pattern until we get down to this a of 2 x squared plus a of 1 x to the first plus a0 x to the 0. But remember, anything to the 0 power is always equal to 1. So in reality, this x to the 0 here just becomes a value of 1, so we often leave that off. So now we're going to describe all of these terms. And I'm going to underline in blue all of these a of n minus 1 terms, a of n minus 2, a2, a1, and a0. All values of a are coefficients. All values of a are coefficients. So this includes a of n minus 1, a of n minus 2, all the way down to a2. Let's put those dots in there. So a of n minus 2, all the way down to a2, comma a1 and a0. All of those are coefficients that must be real numbers. They must be real numbers. So they cannot be imaginary. And we're going to describe one special one here where a sub n, which is this guy right here, is the leading coefficient. So that a of n, that leading coefficient, that leading value is going to be a special term. And then we're going to have to describe something else. We're going to have to describe all of these values up here. So all of these values, n minus 1, n minus 2, all of these exponents. And we could say all values of n. I'll say all values of n, which are the exponents, must be positive integers. So here's where that nomenclature comes in again. We're going to have to make sure we know what an integer means. Remember, an integer which we abbreviate that funny looking z. Remember, this stands in that form of Well, they can be both negative and positive, but for us, when we talk about positive integers, we're talking about the set of 1, 2, 3, 4, and they continue on in that pattern. We could have also called this the set of natural numbers, but for some reason, they like positive integers better. So specifically, where the value of n, which is this guy right here, this attached to that first term, where n is the largest exponent and is deemed the degree of the polynomial. So the largest exponent is considered the degree, and the coefficient of that largest exponent, which is this a of n, is called the leading coefficient. Well, that makes sense. That doesn't seem too difficult. So this is how we describe or define a polynomial. So a lot of times we might get a little worried about all this math nomenclature, but do not fret when it comes to this math nomenclature. We eventually become more experienced with it, and it won't be so tough. So let's go ahead and look at some polynomials. let's look at some examples. So if I were to give you f of x is equal to 2x squared plus 3x minus 4. This is a polynomial. We know that because our exponent is a 2, our exponent's a 1 here, and this is really x to the 0. So all exponents are positive integers because we know we have 2, 1, and 0. We're going to say our leading term is going to be 2x squared. It's going to be the term that has the largest exponent, which then tells us our degree is a value of the largest exponent, which is 2. Our leading coefficient is a value of 2 as well, because that's the value that's attached to that leading term. So this guy is a polynomial. Let's look at another example of a polynomial. Let us say I said f of x equals 3x squared minus 4/3 x cubed plus 5 6x to the 5th minus 1. So notice here, all of our exponents, a 2, a 3, a 5. Remember, this is x to the 0. All exponents, whoa, that's a bright green, very piercing. All exponents are positive integers. We have the 2, the 3, the 5, and then the 0. But the 0, I know that's not really a positive integer. It's an integer that includes 0. However, we'll just say that's a constant value because we know x to the 0 is always equal to 1. Okay, so our leading term, and be careful, our leading term we defined as the term with the largest exponent. So our leading term is actually hidden. It's actually not leading in this circumstance the way that we wrote it. If it was written in descending order, it would be leading term. However, our leading term is 5 6x to the 5th. And that implies that our leading coefficient is a positive 5 6. And our degree of this entire polynomial is deemed by the degree of the largest term, the largest exponent, which is part of the largest term. Our degree is a value of 5. So notice here we have a 5th degree polynomial with a leading term of 5 6x to the 5th, and a leading coefficient of a positive 5x. Leading coefficient of positive 5 6. Let's give some examples of non-polynomials. So if we were to say f of x equals 2 all over x plus 3. Remember, or let's say 2 over x squared. Remember, this is the same thing as me saying 2x to the negative 2 plus 3. This is not a polynomial because this exponent's a negative value. So that's an example of a non-polynomial. Let's look at another example. Let us say I give you g of x equals square root of x minus 2. This is an example of me saying x minus 2 to the 1/2 power. And notice my exponent is another non-positive integer. non-positive integer is not a positive integer. Let's look at a last example. We're going to say 3 all over x minus 2. And here, this guy is a rational function, and rational functions are not types of polynomials. So one of the reasons why we like polynomials so much is because they have a very special quality. Well, actually, they have a lot of special qualities, but one particular to us now is that the domains of all, and very rarely do we use absolute terms like all or every or never in math, but when we do, we should really pay attention to it. The domains of all polynomials are all real numbers. So they have no breaks, no holes, and we're going to learn later, no asymptotes. And that's one of the reasons why we like working with polynomials so much, is because they have a domain that is all real numbers.